All right, we're going to finish up section 2.1 here, modeling with quadratic and linear functions. We are going to do some of the same things that we did in Algebra 2 with modeling of quadratic functions, which was a lot of projectile motion sort of problems. You may remember problems that had the height of a function given its velocity and initial starting position over time would be something like this, with that being the initial height and that being the initial velocity. I mean, that was one of the applications that we did with quadratics. Another one was revenue type of problems, like the one that we have here in example 6. So this says that we have a rental company that has 1,600 units available, of which 800 are currently rented at $300 per month. It says a market survey indicates that each $5 decrease in monthly rent is going to result in 20 new leases. So we want to find out how we can maximize the revenue here for this rental company called Welcome Home. So a good thing to remember here, or to kind of piece together, is that the revenue is going to be the calculation of the number of rooms that we are renting out times the monthly cost per room. So I'm just going to put that there because I didn't really know where else to put it. And then I started making this table over here just to show you kind of how we're going to set this up. You know, if we wanted to find the revenue right now, we would simply then take how many we have right now, 800, and it's at $300 per month. So right now we could take 800 and multiply that by 300, which is going to give us 24,000, but that doesn't even really matter right now. It's just that's how we would calculate the revenue right now. If we did one $5 decrease, according to this market survey, we're going to get 20 more rooms. So instead of 800 rooms, we would now have 820. But we're doing a $5 decrease, so instead of 300, we're actually now only charging $295. If we did two $5 decreases, we gain another 20 rooms. That would put us at 840. But now we would only be charging $290 per room. So there's going to be kind of a break-even point here. Actually, not break-even, a point where we maximize revenue, and that's what we're going to be looking for. So I just did this so that we could easily figure out what sort of expression is going to help us here. Well, if you notice, for every $5 decrease, we go up $20 in our revenue cost, which means from that 800, we can add $20 every time we do a $5 increase. Well, we don't know how many we're going to do, so let's do X. The amount that we are charging per room was initially 300, but every time we do a $5 decrease, obviously that goes down by 5. So what we're saying here is X is the number of $5 decreases, and then we'll use R of X in our equation to represent the revenue. So here's the equation that we're going to have here. The number of rooms, we just said, is the 800 plus 20x. So using my idea from before, that's what we want to use as an expression. The monthly cost is 300 minus 5x. We're going to put this in a standard form. So if you want, pause the video, take a second, multiply, distribute that out, and put that in the standard form. And here's what you should end up getting here. We're going to have, I'm going to put it actually in standard form with our quadratic term first, negative 100x squared plus 2000x plus 240,000. Okay, so a couple of things that don't surprise us at all here. First of all, it's a negative quadratic. Okay, that doesn't surprise us at all because we know that the revenue is going to go up until we hit a certain point when it comes back down again. We want to find the maximum revenue. We want to find the vertex, in other words. The other thing that I want to point out is that value right there. That 240,000, that was the initial amount. Well, that makes sense because remember, the C value of your quadratic equation is your y-intercept. So I might have said 24,000 before. Now we're making way more money than that. 10 times as much. 240,000 right now. Sorry about that. So I'm going to do a little sketch of this graph down here. Go ahead and put this graph into your equation editor of your graphing calculator so you get a nice graph. Okay. I'm going to just do a sketch of it right here. We know that it is going to go through the y-axis right here. I'll just put this as 240,000. Okay, and we are going to be looking for this vertex value right here. Now, if you put this in your graphing calculator, that should be no problem. Okay, you would just calculate the vertex by using your second calculate menu. Once you have it put in, doing second trace, and then doing number 4, doing maximum. Okay, I don't have the actual function in mind, so I can't do it. And then it would ask you for that left bound and right bound, which is where you have to tell it kind of, you know, here's a left bound, there's a right bound, and then it asks you to guess, and then you would guess what that is. And what it's going to do is give you the maximum. Now, if you don't have a graphing calculator and you just want to do this by hand, remember to find the x value of that vertex, find out what this value is right here, you would just do negative b over 2a. Okay, negative b over 2a in this case would be negative 2,000. 2a would be negative 200. So this is just going to be negative 20 over negative 2, 10. And then you would put that back in order to find out what the actual revenue is, what this value is right here. If you were to do that, you're going to find out that that's 250,000. So at 10 $5 decreases, we find out the maximum is 250,000. That's our maximum revenue. So we're going to just fill this out here. Since the maximum revenue is 250,000, $10,000 more than we're making right now, when x equals 10, and I just put C the graph there, which is 10 $5 decreases, that means we're going to be taking $50, 10 times 5, away from that $300. So a rent of $250 is going to result in our maximum revenue there. All right, we're going to finish the section here with just a couple of reminders, really from Algebra 1, just showing with a little bit new notation here. This here, hopefully you recognize, I think I grabbed that right from our Algebra 2 notes. That slope is rise over run, change in y over change in x. Delta y, delta x is another notation we used. And here's the actual formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's vertical change over horizontal change. All right. This is basically saying the same thing. Because remember, this is, if we know that A and B are our x values. If A and B are our x values, then this represents the change in x. And putting A and B into the function would give you your y value. So that represents the change in y. So this is still change in y over change in x, just using function notation. So in example 2, they give you 2 points in function notation. Really, this is just saying our first x value is negative 1, and that y value from that same point is 2. Our second x value, is 3, and our second y value is negative 2. It's just giving you 2 points in function notation. So if we're going to write an equation of line, we would first find the slope by taking one y value and subtracting the other y value, taking the x value that was with that negative 2 as a y value, so 3, and subtracting the other x value. So we're going to have negative 4 over 4 here, which is negative 1. That's our slope. To come up with the equation of line, we use point slope form here, which is y minus y sub 1 equal to x times x minus x sub 1. Okay, a little reminder from Algebra 2 last year, that is just the equation for slope. It's just rewritten in a little bit different way. It's solved for y minus y sub 1. It's like solve for the numerator of that right there. Okay. All right, so we put in one of the points, doesn't matter which one, with our slope. I'm just going to pick the first point there. So y minus 2 is going to equal that my slope was negative 1 times x minus, and then my x value was negative 1, so plus 1. And we're going to distribute that negative and add that 2 over. So we're going to get y equals negative x plus 1. There's our equation for that line. All right, correlation is a measure of a quantitative association's linear strength. Correlation coefficient is R, and R can be anywhere between negative 1 and 1. So from left to right there, we have an R value here that is pretty darn close to negative 1. A perfect negative 1 would be a straight line, a straight negative line with a negative slope. Okay, and then as we go here, we get an R value that is close to 0 in the middle there, all the way to an R value here that is pretty darn close to 1. All right. R equaling 0 pretty much means that there is no correlation whatsoever. On the back side here, I just put a couple things from our textbook that you need to know, you should know. One thing that we haven't done any examples with here in this section, quadratic formula. You probably should know that at this point in time, but just some resources for you. The last thing that we have here is a reminder of using quadratics to model a launched or thrown object. I threw up that equation before. It's really the same one that I kind of have here. Our textbook uses S for height. The one, I usually just use H. I think that makes it a little bit easier. Notice here that it does not say negative 16. It says negative 1/2 times g. That's because g depends on whether we are in feet per second squared or meters per second squared. When I put this negative 16 there, that's because that's half of 32 if you're in feet per second squared. And if it is in meters per square second, then it is actually going to be a negative 4.9 that's there. This is actually a problem here that is kind of a combination of both regression and using that model that we just spoke about. This is asking you to come up with a model for the height and vertical velocity of a rubber ball that has been dropped and or thrown, actually, because our heights are going up and hitting a maximum somewhere in that area right there. So first thing you're going to want to do is put those values into your trusty old TI, whatever you got. And I just did that by putting it into my list. Oops, what am I doing here? I can't multitask. Let's go back here. I just did that by putting it into my list 3 and 4. No, I didn't. I didn't put list 4 in yet here. So as I talk, I'm going to real quick type that in. And you are welcome to pause the video while I do that. Or I'm sorry, fast forward the video while I do that. The magic of YouTube. All right, so we've got all those numbers in now. I put them in list 3 and list 4 so that I could keep my list 1 and list 2 the way they are for working on other examples. What we want to do is graph those two lists, and if you want to do yours in 1 and 2, that's fine. But I'm going to leave mine there, go to my stat plot here. I'm going to turn my first stat plot off, actually, because that's got list 1 and list 2 in it. And then I'm going to go and turn my second stat plot on and make that list 3 and list 4 here. So we'll second 3 and second 4. You don't have to do any of this. If you're just using 1 and 2, you can use what you got. And I'm going to go back to y equals and turn off. This is the equation from list 1, list 2 scatter plot. So I want to turn that off too. So I unhighlighted that equal sign. Now if it zoom 9, zoom stat, it should zoom into that problem that I just typed in. And look at that, it looks like a quadratic regression is going to be necessary here. So we'll go through and do our regression. Stat, calc, we want number 5 for quadratic regression. Now I'm going to make sure I change mine to L3 and L4. And I'm going to store my regression equation in actually y sub 2. So it leaves y sub 1 the way it is. And we'll calculate that. This is going to give us our equation here. And notice I do have this equation actually written down here already. And it looks like we got the same thing as what the calculator wrote right there. So what I'm going to do is just go back to my graph to verify that that fits the data pretty darn well, and it does. Okay, so we know a couple of different things here. We can use that model to help us find the maximum height according to the model. So we're actually predicting that time that it hit the maximum height and what the maximum height actually was. And it looks like it's pretty close to that point, maybe a little bit before that point. So let's do that by hitting our second trace and going to number 4 maximum. I don't know what I did. Let's try that again. Second trace, number 4 for maximum, and it is asking. I think I'm hitting 4 too often here. 3 times the charm. All right, there we go. So we're gonna do a little left bound. Right bound, just you need to be to the left and the right of that vertex. And then for your guess, you just got to be somewhere close. And that's going to tell us that the maximum height according to our model is going to be about 1.8. We are in meters here, about 1.8 meters reached at about 0.4018 seconds. So that's what I'm going to put down here. Okay, little reminder, when you're doing a problem like this, you should be sketching everything that you're doing on your graphing calculator as best as you can. Pretty good. Now we had that nice quadratic going through there. And then I'm just going to put here that we found that vertex happened at 1.8 comma 0.402. And we'll say something like this, that the maximum height according to our model was 1.8 meters reached at about 0.402 seconds. Okay, then it asks us to find the vertical velocity when it hits the face of the CBR. I know that sounds kind of funny when it hits the face of the CBR. When it hits the face of the CBR, that means that it's actually reaching the 0 meters away from what's measuring it, which is the CBR. So we're trying to find out what the 0 is there. Well, to do that, we would have to use our graph calculator again to find out what that 0 is, when it hits 0. Okay, so instead of hitting second trace and doing the maximum, we would do second trace and do the 0. So number 2. And it's going to ask us again for a left bound and a right bound. So we got a long ways to go here. Once you do that, I'm just going to tell you what it is. You're going to find out that 0 is a 1.0222877. That's what shows up on our screen there. That's what the calculator gives us. And I'm just going to real quick see if I can get this 0 here. I'm not sure how far down I got to go because I actually better fix my window so I can actually see the axis. So I need a y minimum that is actually negative. Oh, I don't know if that'll be worth it time purpose wise, but here, let's go up here and take a look at this. What we're going to need for this equation is this velocity calculation that tells us that the velocity after t seconds can be found by negative g times t plus v sub 0. So, negative g of t plus v sub 0 are all things that we can get from our values that the calculator gave us for the regression. The output from our regression, let's see if I get those back up on the screen here. The output from our regression, and I know that I have it already on your paper what A, B, and C are, but there's the output from our regression right there. All right, so I'm going to just leave that. I'm just going to leave that here so that we can use that. We know that negative g over 2 actually equals our a value. So that is what negative g over 2 should be. Okay? Negative g over 2 is our a value of our standard equation. Negative g over 2 or negative 1/2 g is whatever our a value is. So I know that negative g over 2 should equal negative 4.676, which means that g is going to equal, if I double, get rid of that negative sign, about 9.352. Okay, so that is our model's estimation of the gravitational constant there, negative 9.352. Our initial velocity, that is the b value right there. So that's v sub 0. So what we know is that the velocity will be negative 9.352 t plus 3.758 using that equation that I have right there. So if I put what time I want to find that velocity at, then I will have to use that 0 that we have right there for my time. We know that that's how long after it was launched that it hits the face of the CBR, so 1.022 and so on and so forth. We put that in to the function. What we end up getting is that velocity is about 5.8 meters per second, negative 5.8 meters per second, which means it's falling downwards. So the velocity when it hits the CBR, I'm sorry. I don't know why I have CBL written down here, which happens at about 1.0223 seconds, is 5.8 meters per second downward. I don't know if we are going to run into a lot of problems like this where we're actually doing regression and then using these equations, but you should feel comfortable using, for sure, this equation here that we use a ton in Algebra 2 with either negative 16 or negative 4.9 as your leading coefficient.